Welcome to This Explainer. Today we are diving deep into the physics behind the ultimate shapeshifter of modern engineering, the electromagnet. We're going to take concepts that honestly seem like pure magic and break them down into clear, actionable science. Let's get right into it.
To kick things off, I want you to think about a standard permanent magnet. You know, like the kind holding up grocery lists on your fridge. Now, they do their job just fine, but they have a pretty major limitation. They're always on, and their strength is completely fixed. But what if we need something bigger? How do we build a magnet strong enough to literally levitate a massive train, but controllable enough that we can just switch it off the second we're done? Well, we obviously can't do that with a giant fridge magnet. We need a dynamic, switchable magnetic force.
So, here's our roadmap for today's journey. First, we'll look at where electricity meets magnetism, then the anatomy of a solenoid, building an electromagnet, comparing temporary versus permanent magnets, and finally, powering the real world. All right, Section 1, Electricity meets magnetism. Let's travel back for a second to the year 1820. A scientist named Hans Christian Ørsted is running an experiment, and he accidentally places a standard magnetic compass right near a metallic wire. Now, when he passes an electric current through that wire, something totally incredible happens. The compass needle deflects. Up until this exact moment, electricity and magnetism were thought to be two completely separate forces in the universe. Ørsted's happy accident proved that an electric current actually produces a magnetic field. This single observation basically laid the groundwork for everything we're about to discuss. Moving right along to Section 2, Anatomy of a Solenoid.
Okay, so what we're talking about here is a solenoid. By definition, a solenoid is just a long coil of closely wound, insulated copper wire shaped into a cylinder. When you take a straight wire, kind of like the one Ørsted used, and wrap it into a coil, the magnetic fields from each individual loop combine forces. Check out the field lines. Inside, those lines are parallel and straight, which means we have a uniform, incredibly strong field. And outside, well, they curve around, perfectly mirroring your classic bar magnet, complete with a north pole at one end and a south pole at the other. Now, this brilliantly illustrates what's known as the clock rule. If you think about the two circular faces, it's actually pretty intuitive. If the current flows clockwise, that face is the south pole. Anti-clockwise, it acts as the north pole. It's just a simple, elegant rule that gives us total predictability over the magnetic field.
All right, Section 3, Building an Electromagnet. So a solenoid alone is really just a coil of wire. To make an actual electromagnet, we have to introduce a core. By inserting a piece of magnetic material, specifically soft iron, directly inside that solenoid, boom, we create our electromagnet. But you might be wondering, why soft iron? Well, because it is incredibly responsive. It magnetizes intensely the second the electric current flows through the surrounding wire, massively amplifying the field, but, and this is the crucial part, it loses almost all of its magnetism the absolute microsecond that the power stops. It gives us total, on-demand control.
Once we have our electromagnet built, we can actually engineer it to be exactly as strong as we need it to be. If you want to level up the strength, you basically have a few dials you can turn. First, simply increase the amount of current flowing through the wire. More electricity equals more magnetism, right? Second, you can increase the number of turns or loops in the copper coil. Every single extra loop adds its own magnetic force to the total. And third, decrease the air gap between the poles, which concentrates the magnetic flux. So what we have here is a completely scalable system.
That brings us to Section 4, Temporary versus Permanent Magnets.
When we put these two head-to-head, the electromagnet's superpowers become super obvious. I mean, a permanent magnet has fixed strength, right? But an electromagnet strength is completely adjustable and can be scaled up to massive levels. Permanent poles are fixed, but with an electromagnet, if you just reverse the direction of the electrical current, the poles instantly flip. And most importantly, demagnetization. A permanent magnet is always on, but an electromagnet shuts off the very instant you put the power, and that's all thanks to that soft iron core we just talked about, whereas permanent magnets use steel, which stubbornly holds onto its magnetic charge.
Let's look at Section 5, Powering the Real World. Because of the properties we've just uncovered, specifically that ability to safely and instantly control intense magnetic fields, we actually have life-saving medical devices like MRI scanners. These machines generate magnetic fields tens of thousands of times stronger than the Earth's. That's something that is completely impossible to do with standard permanent magnets. But even on a much simpler scale, think of an old-school electric doorbell. When you push the button, you complete a circuit.
An electromagnet turns on, pulls a little metal striker to hit a bell, which then breaks the circuit. That turns the magnet off, letting the striker fall right back. And then it repeats this practically instantly to create that ringing sound. Pretty clever, right?
And then, of course, we have applications on a massive, heavy industry scale. Electromagnets are used in giant cranes at junkyards to pick up literal tons of heavy iron scrap. Think about it. The crane lowers the magnet, the operator flips a switch to turn the current on, it picks up a massive load of metal, moves it, and then they simply turn the current off to drop the scrap instantly. No sticky permanent magnets to try and pry things off of. And, perhaps most impressively, electromagnets are the absolute secret behind high-speed maglev trains. By using electromagnets with reversible polarities, these trains literally levitate right above the tracks. They're propelled forward by magnetic repulsion and attraction, which eliminates friction entirely. It's a real game changer.
So from a simple compass needle twitching on a desk back in 1820 to a train floating above a track at 300 miles per hour today, the journey of the electromagnet is a massive testament to the power of human curiosity and engineering. It really forces us to ask, what other invisible forces are currently being engineered to power the everyday technologies you rely on? Keep your eyes open and never stop questioning the world around you. Thank you so much for joining me for this explainer.